Hello, everybody, and welcome to the Astro Show. I'm your host, Dr. Sam, the founder and executive director of Wyoming Stargazing. Here, you can pick the brains of astrophysicists, get advice from an aerospace doctor, learn what scientists have to say about life, and find out what's going on up above your head, all in the same place. So, thank you for joining us this evening, and we hope that you join us every show, which is the second and fourth Tuesdays of the month at 6 p.m. Mountain Time on Twitch, YouTube, and Facebook. On tonight's show, we have Dr. Jost Migenda, a research associate at King's College in London. Among other things, Dr. Migenda studies neutrinos as part of the Hyper-Kamiokande experiment. We will hear all about that later this evening, but before that happens, let's welcome our co-stars. First, astronomer and data visualization engineer from the Adler Planetarium, it's Dr. Lauren Corleys.
Hello.
Hey, Lauren, good to see you. And next, astronomer and host of her own YouTube show, Nora's Guide to the Galaxy, it's Dr. Nora Bailey.
Hey, everyone.
Hey, Nora. And our special guest for this evening, Dr. Jost Migenda.
Hi, everyone.
Hi,
First time in Wyoming, even if just virtually. So I'm very excited to be here.
Well, we're glad to have you virtually in Wyoming. I'm actually not in Wyoming either, so that's okay. But the show is virtually cast in Wyoming. We were hoping to have Dr. Danny with us this evening, but unfortunately, she is performing a surgery right now. So she is doing her duty to the world apart from being on the Astro Show, even though that is also a duty to the world. Anyways, we are going to get going this evening with Astro Advice. So let's bring up the slides. I don't want to take everybody off. There we go. All right. So here's a little bit what we're going to do this evening. And welcome to Jost. Thanks again for connecting with us in Germany, actually. So it's a little late where you are right now. So thank you for staying up and making this happen. And all right, let's do this. So here is the quote for Astro Advice, life advice from astronomers and other scientists. I'll read it out loud and then give you the option of 4 people who may have said this quotation, and then you can make your best guess of who actually said it. So here we go. Don't let anyone rob you of your imagination, creativity, or curiosity. It's your place in the world. It's your life. Go on and do all you can with it and make it the life you want to live. So that is the quotation. And here are the 4 possibilities. Fabiola Giannotti, Rachel Carson, Mae Jemison, and Rosalind Franklin. And now a little bit about each of them. So first, Fabiola Giannotti. She is an Italian experimental particle physicist who is currently the first woman director general at CERN in Switzerland. B, Rachel Carson, the American marine biologist and conservationist, most well known for her influential work entitled Silent Spring, that really created and advanced the global environmentalist movement. C, Mae Jemison, American engineer, physician, and former NASA astronaut. She became the first African-American woman to travel into space when she served as a mission specialist on Space Shuttle Endeavour in 1992. And D, Rosalind Franklin, the British chemist and X-ray crystallographer who was the first to discover the double helix structure of DNA. So here is that quotation again, and the 4 possibilities. I'll give you a moment, but whenever you're ready to cast your vote, please unmute and go for it.
A is speaking to me this week. That's my
Okay.
choice.
Fabiola and Giannotti.
Yeah.
Giannotti, excuse me.
I'm going to go with B, Rachel Carson, only because I realized when you were showing this that I don't think I've ever seen a picture of Rachel Carson before, and it was very not what I expected. I like it, so I'm going to go with B.
You know, it's funny. I hadn't seen a picture of her, that picture actually. I'd seen others, but that was the first time I came across that picture. So yeah, I like that as well.
And then I'll go with C.
Okay. Go ahead.
Just because the quote is so inspiring that I feel like it needs to be said by an astronaut.
All right. I like that rationale. Well, it turns out the person who actually said this was C. So 1 point for our special guest, Dr. Jost Migenda. Nice work, Jost. So what do y'all think about this? I'm curious to hear.
Curious.
I think it's great. I think it's very true. I definitely think there's kind of a moment for a lot of people when they realize, like, you can literally do whatever you want. It's a little scary, but I think it's really exciting to realize that and be like, you know, we're all just doing the best we can, and you just got to go out there and do what you can. And I think for me, the person that's most often robbing me of my imagination and creativity and curiosity is myself. So it's nice to remind myself to, I don't know, be a little bit nicer to myself.
I will second that, Nora. I am also my own worst critic.
Yeah, I think as you get older, you like fall out of the practice of being curious, right? Like there's almost no child who is not curious and asking you questions all the time. And then you like get into your routine and you're an adult and you have all these things to worry about and you forget to continue to be curious. So much so that I was talking with a friend of mine once, and you know, every time you start a new job, they're like, pick 3 adjectives to describe yourself. And one of the adjectives she always picks is curious. And apparently whenever she says that, like all the other adults in the room are very like, oh, we've never heard someone pick that word before. Because we just sort of forget that we can be curious. So it's something I've been trying actively to do more now. It's just to like ask more questions about what's going on around me. It's how you learn new things.
And I feel like it's so easy to lose that curiosity, because I think as kids, all of us want to be, let's say, astronauts, right? But then when you go to school and you figure out, okay, I need to do a lot of math to go ahead and study astronomy and maybe become an astronaut. In all the, I guess, drudgery of learning math and learning whatever sciences you need, it's easy to kind of lose that will to become an astronaut.
And who better to remind us of that than Jefferson, right? Certainly fits the bill there.
Yeah.
Go ahead, Nora. Go ahead.
Oh, I was going to say, I agree with what Jost and Lauren both said. I think as adults, we often view things through the frame of usefulness. So like, if I learn this thing, how is it useful to me? But it's fun to learn things for their own sake and not worrying about if you're going to remember it in a week or whatever, you know. It's just learn it and just enjoy the moment of learning it, and like how cool that is to know something new. Even if you're going to forget it, it's okay. There's no test.
Yeah, that's actually, I have to say, this is one of the things that I like the most about hosting the Astro Show, because every week I have to delve into all the current events in the astrophysics world for the news quiz. And honestly, I don't think I would do that if I wasn't actually putting the news quiz together. And it is so fascinating. And, you know, it's like an hour or two of my time, but like, I love like finding out like what researchers are up to, you know, what questions are being answered, what new questions are being asked. And I find that perks my curiosity more than like anything else in my current job, running an education, an astronomy education nonprofit. So yeah, I really appreciate the opportunity of sparking my own curiosity every other week, or putting this show together. So that yeah, really rings true for me as well. That it is something that we have to cultivate as adults. Like you said, Nora, like we can become so utilitarian with our jobs just because, timing is so tough and we're all so busy. It's easy just to get caught up, and we just have to get things done. But yeah, I really appreciate the fact that we can spark our curiosity, and it doesn't even take that much effort to do so. You probably are all aware of an amazing Facebook page. I won't actually say the original name of it, but the other name of it is I Really Love Science. Transposed really with a 4-letter word and a gerund. But it is a great, I think, an amazing page that is like devoted to sparking people's curiosity and inspiration and imagination and creativity in the sciences. So if you haven't checked out that Facebook page, I highly recommend it. It is a lot of fun. Any other thoughts on this?
I just to agree with you, that page is ducking interesting.
It is ducking interesting. Oh, ducking interesting. All right. Well, let's with that, I think that's a perfect segue to take us to Astro 365. This day in astrophysics history. So on this day in 1983, the Pioneer 10 spacecraft made it past Neptune's orbit and became the very first man-made object to do so. Which is interesting today, because today we could say that it actually went past the furthest planet because it's the dwarf planet now. But back in the day, it wasn't even past the last planet. It was just past Neptune's orbit back in 1983. And of course, we have the Voyager 1 and 2 spacecraft that have gone much, much farther out in space now, past the heliosheath, past the magnetic boundary of the solar system. At something like, what is it, like 19 or 20 billion miles away, something like that. Or excuse me, trillion. Trillion? No, billion. Billion. Yeah, billion. They are not a light year yet. Yeah, 6 trillion miles would be a light year. They are like a tiny, tiny fraction of that, like not even a light day away. So it is definitely a billion, respectively, I think 19 and 20 billion miles away, but still not bad for a man-made spacecraft. And Pioneer 10 is still out there as well, but it wasn't moving nearly as fast as the Voyager spacecraft that were launched roughly, I guess, almost a decade earlier before Pioneer. So yeah, Voyager are pretty far out there now. All right. That brings us to everybody's favorite part of the Astro Show, the astronomy news quiz. So it's all rapid fire these days. And so co-stars and special guests, as soon as you think you know the answer to these questions, just shout it on out. And going into this, we have Jost with 1 point in the lead. Here we go. ESA, the European Space Agency, just released a never-before look at Mars to commemorate 20 years of which spacecraft?
Is it the Spirit rover?
Save that for another question.
Spoilers.
Spoiler alert.
Mars orbiter?
Not Mars orbiter. I'll give you a hint. It's not slow food, but
Fast.
Another word for fast would be
Rapid.
rapid. Oh, you're getting close.
I have no idea.
Okay. Oh, here's a better hint. This is the name of a place to get your oil changed in your car. Blank lube.
Jiffy Lube?
Not Jiffy, but that is the name of a place to get your oil changed. I was actually thinking of Express Lube. This is the Mars Express. But that was fun. If we have that much fun,
Get your effort on those hints there, Sam.
It was the Mars Express, and what a cool picture, right? It's got the Mariner Valley, the volcanic region up in the upper left where Olympus Mons is. But yeah, super cool image of Mars from Mars Express. All right, so nobody gets a point there. Moving on to the next question. What did the Juicy Watermelon Space Telescope, JWST, just discover surrounding a distant galaxy using the phenomena known as an Einstein ring? This is pretty cool. What everybody is really hoping to find out in space someday.
Aliens?
Not quite aliens. They are hoping to find aliens. This is like the first little marker that there might be life on this galaxy somewhere. Basic, really, really basic building blocks. Before DNA.
Some molecules?
Yeah, organic molecules. We're going to give that to you, Jost.
Ooh.
Yeah, identified organic molecules in the halo around this galaxy. Yeah, pretty cool stuff. So maybe they are hosting their own Astro Show right now, talking about some crazy galaxy that they're dubbing the Milky Way that they just discovered organic molecules in. And someday we'll contact this galaxy. This one's pretty far out there, though. We're talking like, I think it's like on the order of like 5 billion light years away. So maybe not this one, but who knows?
Any day now.
Okay, so that is Jost for 2 points. All right, here is the next question. Which now defunct twin rovers that found evidence of water on Mars are celebrating their 20th anniversary this week?
Spirit.
So Spirit?
Spirit, and they're two of them.
Opportunity?
Opportunity. All right. I think Nora and Jost both said that at the same time. So we'll give you each 1 point. So yeah,
like
Spirit.
inspiring noun rovers on Mars.
I know.
Curiosity, perseverance. Like, no, that's not it.
Yeah. I mean, I feel like we could do better with naming Mars rovers, honestly.
No, I like the names.
I like them, yeah.
Well, that is fine. You are allowed to. Okay, so that is Jost with 3 points and Nora with 1.
And Spirit especially was really well named, wasn't it? Because I think it was originally planned to last for 90 days and then kept on going and going and going.
It certainly had spirit.
It does.
All right, here we go. Bebop 1C detected, and I'm not even making this up, by the way. Bebop 1C detected using ESA's Chile-based espresso instrument and harps is only the second blank system to be observed.
Well, Bebop is searching for circumbinary stars, but we've seen more than 2 circumbinary systems.
Yeah, but this is a special circumbinary.
Ooh.
Is C the exoplanet surrounding those 2 stars?
It is one of the exoplanets, yep. But there's something special about this circumbinary. At least according to this article, it is only the second confirmed multiplanetary circumbinary.
Oh, okay.
Yeah.
That makes more sense.
Yeah. So they dubbed it the Tatooine system for all you Star Wars fans out there. Tatooine was where Princess Leia came from, if you don't know that. Anyways, all right, next question. Here we go. Combining data from the IceCube and Fermi telescopes, researchers found preliminary evidence supporting which version of the grand unified theory? I'll give you a hint. It's not string theory.
The standard model.
Standard model.
Is it?
You're stumping up us this week, Sam.
What was that, Jost?
Is it something with quantum gravity?
It is quantum gravity. Oh, nice one, Jost. Yeah, yeah. So the story is that there's this halo of who was it? No, I don't want to get the details wrong. It has to do with the. One second.
Pop quiz.
I don't want to get this wrong. Hang on here. I got it pulled up. So looking at gamma ray bursts, neutrinos. Oh, they didn't actually explain why. That's why I couldn't remember it. It has something to do with the ultra high energy neutrinos that were detected using these telescopes, that they fit slightly better with the quantum gravity model compared to the string theory model. But they did not go into detail about how they arrived at that.
Interesting. Wait, wouldn't that be the theory of everything then, not the grand unified theory? Wait, what's the difference?
I think they're basically the same. It's the different name for the same idea of figuring out some kind of consilience between the super small theories of quantum mechanics and the or theories of the super small and the theories of the very fast and big general relativity. Put it
Okay.
terms.
I thought grand unified theory was the one that brought all the three forces together, and then to bring in the fourth would make it the theory of everything. But maybe I'm being too ascribing too much intentionality to these definitions.
I think you are indeed correct about that, Nora. I think you are indeed correct. It does include that extra force. Yeah. So it should have said the theory of everything as opposed to the grand unified theory. The grand unified theory is what Einstein was working on and did not complete. But yes, the theory of everything is more correct. So we're going to give a point to Nora for that. So that's 2 points for Nora. And I think...
Why did I get a point for that? I didn't get it right.
Yeah, but you found an error in the questions. I think that's
that's just me being pedantic.
I mean, whatever. Like, I think that's worth the point. All right, so that's Nora with 2 and Jost with 4. Here we go. Okay, although it'll take in the order of a quadrillion years, researchers say that they have discovered a white dwarf star that is in the beginning stages of crystallizing into, not until, and crystallizing into what?
I'm sorry, there's a typo and it says brining stages, and I was just imagining putting a white dwarf like into some salty water.
Yeah, it's supposed to be beginning stages. I don't know what happened.
Very great mental image.
Brining stages. It is not brining. It's crystallizing. The beginning stages of what?
Is it a diamond?
It's a diamond.
It's always a diamond.
Yeah.
A lot of carbon, so that makes sense.
A lot of carbon, and eventually the idea is that it'll crystallize into a celestial diamond. But yeah, in a quadrillion years or so. It's going to take some time. Just to cool off dramatically. So we're talking like several orders of magnitude longer than the existence of the known universe. No big deal.
It's fine.
Okay, Lauren, you got a point. You are now on the map with 1 point. All right, here we go. Still plenty of questions remaining to take the lead, Lauren. Okay. Researchers recently found evidence that the Earth's rotational speed hasn't been gradually getting slower, but rather that it did what for about 1 billion years?
I mean, the alternative to is speeding up, right?
It could speed up, or there's one other possibility, right? It could have sped up, or what?
Stayed the same.
Stayed the same. Nora.
50, 50, 90.
There you go. So apparently for like 1 billion years, it stalled out at 19 hours. Yeah. The length of a day, the rotational period of Earth was 19 hours for about 1 billion years. The interesting
I love that they call it the boring billion.
well, the boring billion, that actually came before. That wasn't about the stalling out of the time. The boring billion is because it was between these two huge changes in oxygen levels in the early Earth's atmosphere. So there was a very low level of oxygen before that and a big spike after it. So it's interesting because now researchers are saying that this big stall, this billion-year stall, was probably related to there being not enough daylight hours for photosynthesizers to create more oxygen in the atmosphere. And it took the Earth's rotation to slow down more so there was more daylight and more time for photosynthesizers to create oxygen to get us to the current levels that we have today.
So
that's why it was the boring. Oh, sorry, go ahead.
Or what kicked it back into decaying again?
Yeah, so it turns out that it has something to do with the fact that during this time, the effect of the sun's gravitational drag, was more pronounced. I don't remember the details, but that's what changed. The moon's drag became more pronounced after this billion years for some reason, compared to before it.
Interesting.
Yeah. Mm-hmm. Yeah. So Nora, I think you got a point for that one as well. So Nora is now at 3 points. Jost is at 4, and Lauren with 1. Okay, here we go. A halo of gas surrounding one of the most distant galaxies yet to be seen by the 2C Watermelon Space Telescope might be ionized by what group of stars? I'll give you a hint.
Population 3 stars?
Population 3 stars. Yeah. Nice. Yeah. So for the very first time, there may be indirect evidence that population 3 stars actually exist. These are the stars thought to have been the very first stars in the universe, which is weird that we call them population 2 stars and not population 1 stars, but
very appropriate for astronomy.
Yeah, I mean, if you think about like the magnitudinal scale for a star's brightness, that's backwards too. So yeah, I guess we're just keeping things consistent. But anyway, so there's this halo of gas around this galaxy, and it's highly ionized. And the two possible explanations are that it's being ionized by an active galactic nuclei in the core of the galaxy, some supermassive black hole, or from a population of population 3 stars. And it turns out that the best fit is with ionization from these super bright population 3 stars, like 500 times the magnitude of the sun. So yeah, they may be hanging out in this the halo of this galaxy. They wouldn't be within the galaxy itself, because the galaxy is believed to be populated by population 2 stars. But it turns out that out in the halo, it may still be possible for population 3 stars to be forming because we're talking about like 400 million years after the Big Bang in this galaxy. So apparently farther out from the galactic core, because temperatures were less out there, it took longer for stars to form. And so it could just be the first generation of stars forming out in this halo as opposed to inside the galaxy.
That's weird, because if it's the really big supermassive ones, you need to sort of be at the center of the halo to have enough mass. So that's confusing. Unless it's like a satellite halo or something, I'm not sure. So
yeah, I actually was curious about that as well, because that was my understanding, and so I didn't quite follow it, but that is actually what they explained in the paper. So maybe that's a critique waiting to happen.
Interesting, yeah.
All right, I think it's all tied up with 4 points between Nora and Jost, and we still have 1, 2, 3 questions left. So Lauren, you can still tie it up here for a tie for first place. All right, here we go. Betelgeuse. What's currently happening to that ill-fated star?
It's getting brighter.
It's getting brighter. Yeah. So yeah, there you have it on the left. A little bit brighter than pictured on the right. It's still probably not going to go supernova anytime soon. But it is doing interesting things. If you remember, it dimmed for a period back in 2020, 2021. It got significantly fainter.
2019, 2020. Yeah.
Okay, thank you. Yeah, 2019, 2020. Astronomers thought that there was a cloud associated with the giant area of sunspots potentially blocking some light, but now it's gotten brighter, like 50% brighter. And Jost, do you know if there's an explanation about why that brightening is happening? I didn't come across one.
I'm not sure.
Okay, fair enough.
I think basically it's just red supergiants are complicated and messy.
Yes. And we can leave it at that. And it's complicated and messy. And we're all hoping this one will explode someday soon, so we get to see a supernova from really close up. What is this one, like 500 light years away? I think it's really, really close. Like neighborhood, solar neighborhood. Yeah, this would be really cool. We're talking like brightness of the full moon for a little while. So that would be nice. All right, let's see. Who got that right? Was that Jost?
Mm-hmm.
That was me.
Okay, so that's 5 points for Jost. Actually 3 more questions. We still have 3 more. Okay, here we go. Still anybody's game. During his life, a Harvard University professor who died 2 weeks ago, tracked down over 600 first and second edition copies of what famous book by Copernicus?
I don't know the title of Copernicus's book.
Yeah.
I'll give you the English, and you'll have to translate it into Latin.
Is it one of those books where the title is like a 2-paragraph?
It is, but I'm only looking for like the first 2 words.
On the revolution of the stars in the
that's it. Yeah, a revolutionary universe. That's right.
Yeah.
On the revolution of the 6 heavenly spheres. Yeah. Excuse me, the 6
bullshitting.
Well, you got it. Sometimes that's all you have to do to get.
Isn't that a life lesson? Yeah.
There is a life lesson, right? Sometimes you just fake it till you make it. And you heard that here, folks, on the Astro Show. So this guy is really, really interesting. I had never heard of him before. His name is Owen Gingerich, and he was way into the history of astronomy and lectured on the history of astronomy. He would sometimes dress in 16th century garb for his lectures, and so known to be really, really engaging. The other fascinating thing about this guy is that he was devoutly religious, and he unabashedly talked about God's hand in the creation of the universe during his lectures. He kept the science like totally legit, and also talked about, his faith that he had. And that is actually what caught my attention in this news article, because the guy who got me into astronomy in high school is a Mormon, and he would also do the same. He was a brilliant teacher, noticed my passion in astronomy really early on, before even I noticed it. And he reconciled the two for himself without a problem, and kept the two separate for us in class as well. But he was really clear about his beliefs and scientific beliefs. And so I thought that was pretty cool that there was at least one other notable scientist out there who had done the same successfully throughout his career, and was known for his great lectures and inspiration. And I thought that was a pretty cool story. And that he had 600 copies of the Revolutionary Omnibus. That's pretty cool too. Apparently he got fascinated with a comment by Arthur Kessler. And if that name sounds familiar, it's from the Kessler effect, which is what the movie Gravity popularized so much. This is like the collision of a couple satellites that then leads to a cascade of collisions that all rain down on Earth. Probably unlikely, but with the proliferation of space junk and satellites, who knows? Maybe Arthur Kessler got it right. But anyways, Arthur Kessler commented back in the 1950s, apparently, that even though Copernicus had published this book, I can't remember the exact date. He argued that nobody actually read it during Copernicus's life, or for a while thereafter. Kessler argued that nobody was actually paying any attention to it for a long time, and that perked this guy Gingrich's attention, and he set out over the next 30 years to prove Kessler wrong, and actually found copies of annotated notes and things that were dated back into the 1600s. And so apparently people were reading this book as early as the 1600s and making note of it. Kind of a cool little part of astronomical history. All right, so 2 more questions. Here we go. The panelists of which controversy? Nora, do you already know the answer?
Well, I don't know what the panel's called, but it's their UAP studies.
It's the UAP panel. Let me read the question. I thought this is really interesting, right? So this is their most recent public announcement, that between only 2 and 5% of sightings cannot be explained by either human activity or natural phenomena. So of all the unidentified aerial phenomena, UAPs, as they're now called, not UFOs, that's old school. Out of all the phenomena seen, only 2 to 5% can't be explained. And so they are expected to release their full briefing over their last year or so of work in about a month. So we should find out more about this guy, which is one of the ones that has not been explained yet. It's in the 2 to 5%, apparently. This was the real famous one by who was a Navy pilot. Is that right? Navy? I got that right?
I think that's right. That sounds right.
Anyways, I don't know. I mean, I think it's cool that NASA is taking this seriously, and who knows?
I think that it's less that 2 to 5% cannot be explained so much as 2 to 5% have not been explained.
Yes. Again, a fine point on semantics.
Just because I get people question me about this a lot.
That's right. Cannot seems a little like, what's the word? Is finalistic a word?
Yeah, definitive.
Definitive. Yeah, it is a little definitive, and it's true. They just have not been explained yet. Okay, well, we have a 2-way tie, 5 points for Nora and Jost going into the last question.
I thought he had 6.
Oh, do you have a 6, Jost? Did I screw up?
Depends on whether you give me a point for the Copernicus book.
Oh, I mean, I guess actually you do. You got it right. You did say about the revolution of the heavenly bodies or something like that.
Something.
Okay, so it is it's 6 to 5.
Give me half a point for that.
No,
Okay.
they got the full point.
Okay, so Nora, if you want to tie, you gotta snag this last question, and it's gonna be one of these ones that's gonna be a quick answer. All right, this is pop culture stuff here, so it's anybody's game. All right, are you ready? Here we go. Last week, United Launch Alliance successfully tested the first stage of their new super heavy rocket named after this famous Star Trek character's home planet.
Spock?
And the planet name?
Vulcan?
Vulcan!
I'm not a Trekkie. I've seen like 2 of the movies with Chris Pine, and then that's it. I admit.
Nicely done, Nora Bailey.
I can do the hand thing, though.
win. There you go. All right.
For the tie, for the win.
Oh, that's right. Oh, we decided we're giving Jost a full point, so it is for the tie. That's right. So tie for the champion of the news quiz this week, Dr. Nora Bailey and Dr. Jost Migenda. Nice work.
Hey, high five.
All right. Well, we've got about 20 minutes left, and our special guest. Oh no, sorry. I always forget this. What's up, Dr. Sam? I always forget. Like it's like the one part of the show that's named after me, and I forget that we actually do it. I don't have anything new to report. This is exactly what I talked about last time. So if you didn't get out and see Mercury and Jupiter in the early morning sky, you still have a chance. It's really, really cool. Jupiter is up about an hour before sunrise, basically looking due east. And tomorrow is going to be a really cool conjunction with the moon, crescent moon. And so definitely worth taking a look at that. Oh, my dog just decided to open the door. That's great. You learned how to do that recently. And then the other dog is in as well. All right, hello, boys. And then looking northeast, a little bit before sunrise, half an hour, you can catch Mercury in the next couple mornings as well, really close to the horizon. So you have to have a pretty unobstructed view of the horizon to see Mercury down there, a little bit to the north of where you see Jupiter. So if you're an early bird or you just stay up all night and check it out before you go to sleep, it's definitely worth a peek. All right, so now welcoming our special guest, Dr. Jost Migenda. Thank you so much for being here. We really appreciate your time on the Astro Show. I think we've got a couple slides that you wanted to share with us. So I'll pull up the first one, and yeah, you can tell us a little bit about it.
Sure. Thank you for having me. And I must say, I always feel like kind of an imposter when I'm on an astronomy event, because I'm not an astronomer, right? I do astroparticle physics. So I study astrophysics using fundamental particles. So I'm kind of using some of the smallest things in the universe to study some of the largest, in my case, stellar explosions in the universe. So you've got these 2 completely different size scales, and yet if you put them together, they actually work together really well, and we can use them to study the universe. And that's what blew my mind when I first got into this area back in undergrad. And so today I want to take you to Japan, somewhere in the mountains, about 150 kilometers northeast of Tokyo. You can see panorama here. And now my question to you is, if you were to build a detector there to do astronomy, where would you build it?
Well, knowing a little bit about what you study, I'm going to say you would build it underground.
You're very
You're gonna steal
right.
their thunder like that.
See, I was
Yeah, there are
hoping
no
for
rhetorical
how
questions
we
here
build
on the
our
Astro
telescope
Show.
on top of the mountain. But no, you're completely right. We are actually going deep underground below one of these mountains. And that's because we're looking for these subatomic particles called neutrinos. And the easiest way to imagine neutrinos is they're kind of like ghosts. They can literally go through walls because they interact so rarely with other matter. And so if you build your detector down inside a mountain, you've got this whole kilometer of rock shielding you from everything else, from cosmic rays that are constantly raining down on the atmosphere. And all those get stuck somewhere in the mountain, and only neutrinos can actually make it through and enter your detector. And so we've got this detector deep underground, and you can see on the right here on this slide, that's the inside of the detector. It's basically this giant cavern that's usually filled with ultra pure water. And then every once in a while, we're lucky. Most neutrinos go straight through without leaving any trace. But every once in a while, we're lucky, and one of them will actually interact and, for example, give one of the electrons in the water a little kick, like colliding billiard balls. And then we've got these photosensors all over the inside walls of this detector, which are these kind of golden bulbs, golden semispheres, really, really huge, like 50 centimeters in diameter. And they basically act like a reverse camera. Sorry, like a reverse light bulb. So instead of taking electricity, turning it into light, they take light, even just a single photon, so very weak amounts of light, and they turn that into an electrical signal we can read out. So we can basically take a photo of this neutrino interaction with all these sensors covering the detector walls. And that way we can study, for example, from how bright the flash of light was, we can study how much energy the neutrino had, or we can at least approximately figure out which direction it came from, stuff like that. So we can actually do astronomy with that. And we can study, for example, our sun produces a lot of neutrinos as part of nuclear fusion. And we can observe those and study, for example, what the temperature inside the center of the sun is, and measure that quite precisely, about as precisely as I know the temperature outside my house. And me personally, I use this detector, or actually a future one called Hyper-Kamiokande, which is currently under construction. So the one you see here is actually the predecessor called Super-Kamiokande, because we're very creative. So yeah, I work on this next generation detector that's currently under construction. That's going to be even bigger, like a 70 meters tall, 70 meters in diameter cavern. So one of the biggest human-built underground caverns overall. And I mostly use that to look at supernovae and to figure out how these massive stars explode. And if we go to the next slide. Yeah, this is actually a photo from back in March from our previous collaboration meeting. Because I just wanted to highlight that this is not just me, obviously, building this detector, but it's this whole multinational collaboration from, I think, about 20 countries all over the world, actually that map is not quite up to date anymore, because Australia just joined earlier this year. So we've got over 500 people from all over the world, all these different countries, working together on building this detector. And I think it's so important to highlight just what a huge undertaking that is, and how important it is to collaborate with colleagues all over the world, maybe specialize in different areas, and can build different components of the detector. And of course, the side of that is you're spread all over the world, so you have a lot of these video conferences. So we've been using Zoom long before the pandemic, before everyone else started doing that. And you can imagine, because of time zones, it's almost impossible to find meeting times that work for everyone. So I've had meetings that go past midnight, actually like the one right now, like the show we're doing now. Or I've had meetings where I had to get up at 6 a.m, which to me is even more painful. So yeah, this sort of international collaboration has some downsides, but in general, it's a really cool experience to come together and build an experiment of this scale. And then on the final slide I have, so I mentioned I work on trying to figure out how supernovae explode. But that's not just me. So there are a bunch of other neutrino detectors, which also try to detect neutrinos from supernovae and learn something about them. And actually, over 20 years ago now, a bunch of these experiments came together and developed what we call the supernova early warning system, or SNOOS. And SNOOS is kind of meant as a wake-up call for astronomers. And this is where I hopefully get some of the astronomers watching back on board again, who are getting slightly tired of all the particle physics. Because if in one neutrino detector you see a bunch of events all at once, it could be a supernova, hopefully, but it could also be just some random accidental background, or it could be you left a calibration device in the detector accidentally, because we're human, right? That happens. So one detector can make a mistake like that. But if multiple detectors all over the world, in different places, different time zones, all see a burst of events at almost the same time, that can't just be a random coincidence. That can't just be some mistake. That's got to be a supernova, right? So we've got this network of, right now it's about 7 detectors all over the world. You can see in North America, some in Europe, in Japan, and then IceCube at the South Pole, which we actually talked about earlier in one of the questions. So you've got all of these neutrino detectors all over the world, and when they see something that might be supernova, they send it to the central SNOOS server, and if multiple detectors see something at the same time, we send out a public alert to astronomers to make sure they get their telescopes ready, because neutrinos actually arrive a little before the light, simply because they are produced right at the start of the explosion, before the actual explosion becomes, before the shockwave breaks through the outer layers of the star and becomes visible. So neutrinos connect as this early warning system for astronomers to observe a supernova. Yeah, I think that's the gist of what I'm working on.
That's very cool. I love the acronym SNOOZE. First of all, that's fantastic. Very appropriate. I'm curious about.
By the way, back when colleagues of mine originally worked on this, they had some trouble deciding on the name and came up with lots of ideas. One of them was point over there at that old exploding star. Maybe it's to potatoes.
Oh, I really wish that's what they would have gone with. Oh,
Although
that
I,
would have been so
I
much
think
better.
it's harder to get astronomers excited about potatoes. So
Wow, that is brilliant. Potatoes. Anyways, snooze.
you say potatoes, I say snooze.
Oh, nice. Okay, so how much sooner do neutrinos actually make it compared to visible light from a supernova? I mean, I assume that like the gap depends on distance, but what are we talking about?
So it depends. Actually, it just depends on the size of the star.
Oh, okay.
So the neutrinos themselves, they do have a mass, but it's so tiny, like millions of times lighter than an electron. Actually, it's so light we don't even know what it is. We just know a kind of upper limit. So they travel at almost the speed of light.
Right.
And they lose, maybe if they travel across the whole Milky Way, they might lose a few milliseconds compared to light.
Oh, wow.
But so what determines the time difference is basically how compact the star is. So if it's there's this type of star called Wolf-Rayet stars, which basically have blown up all of the outer shell already. So it's a pretty small, pretty compact star. So the shock wave just takes a minute or so after the explosion takes place in the center of the star, and all the neutrinos are emitted. After that, the shock wave only needs about a minute or so to reach the outer layers of the star and break through. And this, what's called the shock breakout burst, is what we see. Whereas in other stars, like red supergiants, it can take the shock wave a few hours or up to a day or so to actually reach the outer layers of the star.
So if you snooze, you lose, but maybe not with this snooze.
Exactly.
Thank you for humoring me there, Jost, even though I totally stole your thunder with your underground research. I've been known to put my foot in my mouth at various times. And so, yeah, my apologies for doing that. I don't know what I do sometimes. But anyways, Jost, this is really, really fascinating stuff. Super cool. And I really appreciate the fact that you took the time to describe why studying the super, super small stuff, neutrinos, is relevant to understanding the really, really big stuff like supernovae and stuff about the universe as a whole. So thank you for doing that. One of the questions that we'd like to ask all of our special guests is, what's the one thing that you wish everybody would ask you, but nobody ever does?
And at least in academia, I wish people would ask me about the software I develop, right? Because when I go to a conference, a lot of people will ask me about the physics and about experiment and about my, whatever analysis method I use. but very few people actually ask about the software I'm developing to do these studies. And yet, actually, software is so important to, I mean, not just astrophysics, but especially astrophysical research. And I think we don't spend enough time kind of thinking about the software and things like, writing good code, or sharing our software as open source, so we don't have to reinvent the wheel every single time, and probably make a few bugs while we're reinventing that wheel. So yeah, I wish people cared more and thought more about software and asked me about it.
Well, Jost, I would love to hear about the software that you're developing for this research that you're working on.
I'd love to tell you, but how many hours do we have left on the show?
You have -1 minute, actually, but no, I honestly would like to hear about it. So take all the time you'd like. We're good.
Sure. So actually, for studying supernovae, a lot of what we do is we rely on computer simulations, right? Because these neutrinos are so hard to detect, they so rarely interact with normal matter, that we need a very close by supernova, ideally somewhere within our Milky Way, to actually observe enough neutrinos from that. And those happen very rarely. Like, we might get 2 or 3 supernovae in our Milky Way per century. So a lot of what we work with is computer simulations, where there's a couple of different groups all over the world who are using these giant supercomputers and input all the detailed physics and the what the structure of the star looks like immediately before the explosion, and then they simulate kind of millisecond by millisecond. Okay, what happens next? What happens next? And try to get an actual explosion out of that. And so one of the pieces of software that I'm working on offers you tools to work with these explosions. So, for example, all these different groups use different formats in which they give us the outputs of these simulations. And that tool combines them all into a consistent format, which is really nice to work with. And then it lets you apply transformations to determine how the flux of neutrinos changes between the supernova, where they're emitted near the center of the star, and then as they exit the star and travel to Earth, how do these neutrino fluxes change? And then finally, it gives you a way to simulate, based on that neutrino flux, what you would see in a realistic detector on Earth. Right, where your detector maybe isn't perfect. So the energy resolution, the energy reconstruction isn't perfect. You get some smearing effect there. Or you might be, depending on the detector material, you might be more sensitive to some types of neutrinos, stuff like that. So it's this package called Snoopy, combining Snooze and Python, the programming language, which is this kind of full tool chain from start, from those computer simulations, all the way to what you're actually observing in detector on Earth. And that's actually the biggest piece of software I'm currently working on.
Very cool. And that was like the most.
That's open source. And if you're watching this, you work on anything related to supernova neutrinos, please look up Snoopy or contact me if you have any questions. Sorry, I had to include that advertisement.
Totally fine. Thank you for doing so. We should always plug our own work. I think that's fantastic. That was the most brilliant explanation of a piece of software that I think I have ever heard. That was fantastic. Nicely done. And well worth the time. So speaking of time, we are just about out of time, or in fact, well over time. But I always like to give the last word to our special guest. And so Jost, if you have any words of wisdom or advice that you would like to impart on budding particle physicists or astrophysicists or both, then I would love for you to share that with them.
Yeah. And my advice, especially if you're just entering the field, just starting to study astrophysics, astronomy, is that just so much of science is dealing with frustration, right? I think couple of weeks ago, I was talking to an early PhD student who was pretty exhausted, and who was saying, basically every time I learn something new, I immediately smack into a brick wall again. It's so frustrating. Is that normal? And I told her, yeah, that is science, right? And as long as you're smacking into a new brick wall regularly, not into the same one again and again and again, you're doing just fine, right? Because I think if you haven't done a PhD in probably astrophysics, or it's probably true of a lot of other fields as well, I think what you underestimate is that so much of it is not just about doing astrophysics, but it's about learning these 3 statistical methods, and then getting to know these 2 Python packages you need for your data analysis, and then suddenly you have to learn a bit of Fortran, which is a very old programming language, because there's this one essential script that's been handed down from PhD student to PhD students for 30 years now. No one quite understands anymore how it all works, but somehow it does work, and you better not break it. And of course, that's written in Fortran, because back in the 90s, that was considered modern. And so you have to learn Fortran, right? And then there's lots of other stuff, like working with these computing clusters, or various bureaucratic procedures at your department, or version control with Git, and so on. There's just so much stuff you need to learn when you do an astrophysics PhD that's got nothing to do with astrophysics. And it's incredibly frustrating a lot of the time. But you are, feel like the best way to put it is, you're not actually doing a PhD in astrophysics. You're kind of doing a PhD in problem solving with occasional applications to astrophysics. And it's frustrating, but at the end, you will get somewhere. And you occasionally get to do astrophysics once you hit all those other brick walls. Sorry, that was kind of rambly.
No, it's okay. I mean, probably the most straightforward, practical, realistic advice that you can offer to PhD students, but maybe anybody just starting to delve deeply into whatever their field of study is. So I think that's great. Co-stars, do you have anything you want to ask Jost or tag on to that from your own experience before we say goodbye to everybody tonight?
No, just that I agree. I had that same experience. It does get easier as you start to learn things. So in the beginning, it's really tough.
Yep, I co-sign.
Yeah, indeed. So true. Well, Jost, thank you so much for being with us this evening. It has been an absolute pleasure chatting with you.
Having me, I had a blast.
Okay, good. I'm glad to hear that. Even at the late hour that you are offering your time, I'm glad that you're still having fun. And our operations director, Maggie, will reach out to you with a thank you gift. So thank you so much again for your time this evening.
Thank you.
Yeah. And thanks to the co-stars. As always, we would not have the show without you. I really appreciate your time and expertise, wit, etc. Thanks so much for being here. Thanks to the folks behind the scenes, Maggie, our operations director, Yamako, helped put together the slide deck, and our board of directors, and everybody else who supports Wyoming stargazing, including you who are watching live or who will watch this recording later on. We appreciate your support as well. And so until next time, we hope that you are well, and we'll see you again in a couple of weeks. But until then, don't forget to look up. We'll see you next time.